Welcome to College Algebra. In this lecture video, let's take a look at inverse functions. All right. So before I start explaining the word inverse function, I would like you to take a look at the concept of an inverse relation. The inverse relation, okay, is actually referring to the interchange between the x and the y coordinates, or is the interchange between the x and the y variables. Okay, so inverse is about interchange between the x and y variables or x and y coordinates. So here I have a relation, my blue parabola, y equal to x squared minus 5x. So if I want to know what the vertex is down here, y equals x squared minus 5x. So let's do the negative b over 2a. That will be negative 5 over 2 times a, which is 5 over 2, which is 2.5. All right, just to say that's 2.5 for right now. All right, to find the y value or the k of my vertex, let's substitute back my 2.5 back into the function. So that will be 2.5 squared minus 5 times 2.5. Just trying to see what the y value is. Minus 5 times 2.5. Okay, negative 6.25. So the y value of the vertex is negative 6.25. All right, so interchange between the x and y coordinates or x and y variables. So my pink parabola open to the right is the inverse of the blue. So interchange between the x and the y variable. So now rather than having y equals x squared minus 5x, if I interchange between the x and y variable, it will be x equal to y squared minus 5. So that means at the same time, the same vertex for the blue it is also going to become the vertex for the pink parabola. But since the pink parabola is the inverse of the blue, that means the coordinates will actually be interchanged. So the x value for the blue now become the y value of the pink. The y value of the blue parabola now is going to become the x value. So if you kind of eyeball it, you can tell this point right here is about negative 6.25 and up about 2.5. All right, so that's the basic concept of an inverse relation. It's about the interchange between the x and y variable or the x and y coordinates. So here I have 1, 2, 3, 4, 5 different points together. It's called a relation. So if I want to find the inverse relation, then all I'm going to do is interchange between all the x and y coordinates. So then I would, for the 2 comma negative 3, the inverse will be negative 3, 2. And this one going to be 2, 4. 3, negative 3. Negative 1, negative 2. And negative 4, 4. All right, so these 5 points will be the inverse relation as compared to my original z equal. All right, so the domain for my inverse, find the domain and write as a set notation. So for the inverse, that will be domain will be the x values. So that will be negative 3, 2, 3, negative 1, and negative 4. All right, so the range of the inverse now will just be the y value. That'll be 2, 4, negative 3, negative 2. All right, I'm not going to write 4 twice. All right, that's all it is. So this page right here, I just want to begin to talk about the word inverse is about the interchange between the x and y variable or the x and y coordinates. Let's take a look at this concept called one-to-one. A function f is a one-to-one if every pair of the distinct elements of x1 and x2. So that means here I got 2 x values, okay? 2 distinct x values in the domain. of f, then f of x sub 1 cannot equal to f of x of 2. So basically, I have two x value, x1, x2. If I substitute them into the same function, okay, then f of x of 1 is referring to the y value cannot equal to the y value where I substitute x of 2 into the same function. So if I have two distinct x values called x1 and x2, then the y value of the two and the y value actually cannot be equal. All right. This means that every element in the range of f paired with exactly one element of the domain of my function f. So as you can recall, for a function to be a function, we can't have the same x value. All right. Can't have the same x value. So here, since my y value cannot be the same, okay, since my y value can't be the same, for a one-to-one function, you just can't have the same y values. Okay, you remember? Can't have the same x value to determine whether a function is actually a function, not a function. To determine if my function is a one-to-one function, we just cannot have the same y value. All right. So what we used before to determine whether a graph is a function, not a function, we use the vertical line test. So here we are introducing what we so-called the horizontal line test. Okay, horizontal line test is used to determine if the graph of function is one-to-one. If the horizontal line crosses the graph of a function more than once, if it crosses more than once, it means I have the same y value again. Okay, then the function is not one-to-one. So is this okay? Let's think about this. If I pretend I have two y value, okay, and matching up with two distinct x value, then this is actually not one-to-one. This is actually not one-to-one anymore. Okay. If the two x values are distinct, then the two y value got to also be not equal. Now, can I have two distinct, can I have two of the same x value, but two different y value? Yes, this is okay. This is actually referring to as one-to-one. Okay, one-to-one function is where we cannot have the same same y value. So if you actually plot these 2 points, this is actually a vertical line. Vertical line is actually a one-to-one function. Okay, it's actually a one-to-one function. But normally we don't call it a vertical line as a function anyway. But vertical line does pass the horizontal line test because if I draw a horizontal line through it, it will only touch it one time. Therefore, it determined that graph is actually a one-to-one. Okay, so we're going to start drawing horizontal line and make sure that it does not cross over the graph more than one time. If it does, that means I have the same y value. Therefore, it is not one-to-one. So back to this picture, my blue parabola. Okay, my blue parabola. If I actually do a horizontal line test, draw through it, it actually end up with two of the same y value. These two y values are exactly the same, but the x values are different. So parabola is actually not one-to-one functions. It's actually not one-to-one. Okay, so let's check it out. Okay, let's draw these pictures and then let's see if they're past the one-to-one. Okay, well, let's see if they pass the horizontal line test. If they do, that means they are one-to-one functions. So let's solve for y real quick before we punch in the calculator. I'm going to move my negative 7y to the third over. So that will give me x equal to 7y to the third. Divide both sides by 7. That's y to the third equal to x over 7, or 1 over 7x. Take a cube root on both sides. So my y is now equal to cube root of x over 7. So this is a cubic function. All right, cubic function normally looks like this. All right, so does that pass 1 to 1? The answer will be yes, it does. So let me graph it for you. X over 7. All right. So it looked like certain part where the y values, it looked like a horizontal line. So most student does not think it's going to pass a horizontal line test. But if you actually look on the table, you don't see any y value are exactly the same. They are very close to each other. Okay, that's why the graph appear to be like a horizontal line, but it's really not. Okay, it just kind of rises. Okay, very very slowly. These decimals are so close to each other on the graph, it just make them look like a horizontal line, but they are not. Okay, so if I draw a horizontal line through the graph, it will only touch it one time. Therefore, cubic function is 1-to-1 functions. All right. This one, let's see. Get y by itself, move the x squared over. So that should give me y squared equal to negative x squared plus 1. Take a square root on both sides. My answer should be positive negative square root of negative x squared plus 1. So we graphed this function before. Oh, sorry. Okay, let me do the positive square root first. Positive square root of a negative x squared plus 1. And then I'm going to type in a negative square root of negative x squared plus 1. So put the two pictures together. It actually give me a circle graph. All right, let me go from negative 5 to 5 real quick. All right, circle graph. If you draw a horizontal line through it, it's actually not going to be 1-to-1 because it's going to touch the graph more than once. So it's not 1-to-1. All right, not a 1-to-1 function. All right, let me square both sides here first so I can get y by itself. So this is going to be x squared equal to 3 minus y squared. All right, move the y squared to the left, x squared to the right. So that will be y squared equal to negative x squared plus 3. So take a square root on both sides. My x, excuse me, my y is again going to equal to positive negative square root of negative x squared plus 3. So this is basically the same as that. So this should give me another circle graph looking picture. Negative x squared plus 3. Just change it to plus 3 here real quick. There you go. All right. Again, not 1-to-1. So that's a circle graph. All right. Okay, y by itself. If I do a little quick cross product, 7y times, x times 5y minus 1. Let's write it this way for a minute. 7y times 1, 7y plus 3 times 1 is 7y plus 3. Since my variable term 5y is trapped inside the parenthesis, I got to do a distribution to bring it out. So that gave me 5xy minus x equal to 7y plus 3. All right, let me move the 7y over, negative x back. So that gave me 5xy minus 7y equal to 3 plus x. All right, so since my y is trapped between two terms, the only thing I can do is factor out my y. So that will be 5x minus 7 equal to 3 plus x. So divide both sides by the coefficient 5x minus 7. All right, so this is actually a rational function. So let me graph my rational function, see if it's a 1-to-1. parenthesis 3 plus x divided by parenthesis 5x minus 7. Okay, again, okay, as the x keep on going to the right or left, it looks like it's kind of horizontal, but it's not. Okay, it's just the y value again are so small between any given two x value, okay, that it appeared to be like a horizontal line. So if I draw a horizontal line through it, it will actually only touch it one time. Okay, so rational function, this particular rational function is a one-to-one function. All right, I don't have to graph this one. Everybody can see this is an absolute value function that will open up. So the V opens up. It's not going to be what? It's not going to be one-to-one because I cross it twice. All right, to the fourth power. I don't think we ever done one like this. We will actually start introducing higher exponent than 3 in a different week here. Parenthesis negative 3 plus x, whole thing to the fourth power, plus 1. Sorry about that. I'm going to go back to the extended window. All right, it's a U-looking graph, okay? So if I draw a horizontal line through it, it's actually not going to be what? Not going to be one-to-one again. Okay. All right. So those are horizontal line tests. Now the inverse function, okay? What's the big deal about the horizontal line test? If a function f is one-to-one, if I pass a horizontal line test, then a formula for its inverse can be found as follows. Okay, so you got to pass horizontal line first in order to actually find the inverse function. So the inverse function of f is denoted as f inverse. Okay, this is not f to the negative 1 power. This is called f inverse. All right. So once I know my function is a one-to-one function, then I'm going to follow the 4th step to find its inverse function. All right, replace the f of x with the letter y, interchange between the x and y. This is the key right here, interchange between the x and y variable. Then I'm going to solve for y. And once I get y by itself, then I'm going to replace my y with f of inverse of x. Okay, that's how we obtain. This is actually how we're going to find the inverse function. Okay. Now, what happened with this parabola? Okay. What happened with this parabola that is not one-to-one? Well, I can still find its inverse relation. Okay. I just cannot find its inverse function. So the inverse relation of my blue parabola is the pink one. But think about it. The pink parabola is actually not a function anyway, because it does not pass the vertical line test. So there's a difference between using the word relation versus the word function. Okay. So if I don't have an inverse function, that's okay, but I can still have what? Inverse relation. All right, so let's give this a try. This is a cubic function. X to the third. Normally x to the third will either look like this or look like this, as I've shown y'all before. Either way, when I draw a horizontal line through it, you'll only touch it one time. So I know my cubic function is what? One-to-one. Earlier we had a cube root function. This is a cubic function. All right, first step, replace f of x with y equal. All right, second step, interchange between the x and y variable. So now it will be x equals negative 4 minus y to the third. All right, step number 3, solve for y. I'm going to move my negative y to the third over, move my positive x back. So that will be y to the third equal to negative x minus 4. To get y by itself, I got to take a cube root on both sides. So my y is equal to cube root of negative x minus 4. All right. So once I got y by itself, step number 4, replace y with f of inverse of x. So my inverse function is cube root of negative x minus 4. So let's graph it. All right. Tell you what, I'm going to graph the original cubic function, negative 4 minus x to the third. Okay, this is what the original cubic function looks like, one-to-one function. Now on the y2, I'm going to draw its inverse, which is cube root of negative x minus 4. So cube and cube root function, okay, are inverse to each other. So these cube root and cubic functions are inverse to each other. All right. So this is a cubic function. Start out with, and then my inverse function got to be x to the third power. Got to be a cubic function. So for a cubic function, I showed you earlier, cubic function is what? What is that cubic function I drew? Cubic function, okay, is actually a one-to-one function. So I'm going to find its formula. I'm going to find the formula for its inverse. So step number 1, replace f of x with y equal. Step number 2, interchange between the x and the y variable. So now my new equation will say x equal to cube root of y plus 5, then plus 2 on the outside. All right, need to get y by itself, but so I need to isolate my cube root term first. So I'm going to move my positive 2 over. So that will be x minus 2 equal to cube root of y plus 5. Now to get rid of the cube root, I got to cube both sides. So I'm just going to cube it like this. I'm going to write it like this rather than multiply it out. So then I should have x minus 2 whole thing to the third power equal to y plus 5. So move the positive 5 over. My y will equal to x minus 2 whole thing to the third minus 5. All right, so this is a cubic function. All right, you can look at it, you can tell the function has shifted to the right 2, down 5. All right. So fourth step, replace my y back into f inverse. So the inverse function of my cube root originally is x minus 2 whole thing to the third minus 5. Okay, that will be fine. All right, let's just show you that earlier the rational functions are one-to-one functions. Okay, so let's find the formula for its inverse. All right, so step number 1, replace f of x with y equal. Step number 2, interchange between the x and y variable. So that will be x equal to negative y plus 4 over y plus 3. Step number 3, let's solve for y. All right, so same technique as earlier. X means x over 1. I can just use a little cross product. And then I should have x times y plus 3 equal to negative y plus 4. Okay, since my y is trapped inside the parenthesis here on the left side, I got to do a distribution to bring it out. So that's xy plus 3x equal to negative y plus 4. All right, variable term y on the right and the left, make sure they're on the same side. So I should get xy plus y equal to negative 3x plus 4. Since the two terms are not like terms, I can just factor out a y. So that will be y times x plus 1 equal to negative 3x plus 4. All right, to get y by itself, I got to divide both sides by the coefficient. So my answer, y equals negative 3x plus 4 over x plus 1. So step number 4, rewrite it as f inverse. So my inverse function here is going to be negative 3x plus 4 over x plus 1. All right. This is a square root function. Okay, very interesting little problem, which I will do another example here shortly. All right, so square root problem. If it goes this way or if it goes that way, it is still considered as a one-to-one function. Again, it appeared to be flat. Part of the graph appeared to be flat because the y values are so close to each other. It makes us think that this is actually a horizontal line, but it's not. The y value is never the same on the square root functions. So it is a one-to-one function. All right, so let's find its formula. Y equals square root of negative x plus 3 minus 2. All right, interchange between the x and y variable. That will be x equal to square root of negative y plus 3, then minus 2. All right, move my negative 2 over. Begin to solve for y. That's x plus 2 equal to square root of negative y plus 3. All right, square both sides. So I'm not going to actually multiply it out again. So this is going to be negative y plus 3 equal to x plus 2 whole thing squared. Since my variable term is negative, I'm going to move this over here to the left side, become positive. Move the x plus 2 whole thing squared to the right. That's negative x plus 2 whole thing squared, and then still plus 3. So this is actually going to be a parabola, right? Open downward. Okay, very strange. I'm going to graph both of them. If I say square root, oh, sorry. Oh, okay, never mind. I square on both sides. Square root of negative x plus 3, close parenthesis, then minus 2. And then my inverse function here is negative parenthesis. Oh, then, you know what? Let's graph the square root function. Look like that. Now, y2, negative parenthesis x plus 2 squared plus 3. So the inverse of my radical function is actually that. Okay. All right. So everything look legit. All right, so step number 4. By the way, I don't know if you ever noticed, this button right here, what I use for square root, it's actually on the x squared. Why the two buttons together? Well, because these two commands is actually inverse to each other. As a matter of fact, the entire graphing calculator, most of the inverse operation is always on the same button or right next to each other. Just like multiply and divide are inverse operation, so they goes together. Okay, this is why the calculator buttons are laid out a certain way. All right, so my inverse function is going to be negative parenthesis x plus 2 squared plus 3. All right, so let's take a look. All right, consider the following function is 1-to-1. So I'm telling you that this rational function is 1-to-1. Find the inverse function by following the 4-step. Okay, so let's find the inverse function of this. So number 1, okay, replace f of x with y equal. Step number 2, interchange between the x and y variable. Number 3, solve for y. So I'm gonna use another cross product. Can't really use cross product because right now I got 3 terms. So tell you what, let's move the negative 3 over first. So that becomes x plus 3 equal to 4 over y. Since my variable y is in the denominator, so to bring it upward, I will need to multiply every term by y. But instead of times every term by y, I'm going to write it as these 2 terms together viewed as one factor times the y. All right, the y cancels out. So that becomes y times x plus 3 equal to 4. I don't want to distribute. I do not want to multiply this out because right now my y is already actually isolated as a single factor in this term. So to get y by itself, all I'm going to do is divide both sides by the x plus 3. So that's 4 over x plus 3. So my inverse function is 4 over x plus 3. Now, the second part is the composition of the two functions. Find f of f inverse of x. So that means I need to substitute the inverse function into my original function f. So my original function f, let me write this down first, is 4 over x minus 3. So if I do an f of f inverse of x, okay, that means substitute the f inverse into function f, wherever you see an x. So that becomes 4 over x plus 3, and then minus 3. Okay. Now let's simplify this a little bit. 4 divided by this means 4 times the reciprocal, which is x plus 3 over 4, then minus 3. So now the first term, top 4, bottom 4 cancels out. That leave me with the first term as x plus 3. But I still got this minus 3 here. So combined like term is equal to x. All right, vice versa. Now take the function f and substitute into f inverse. So let's go backwards. Wherever I see an x. So f inverse of f of x is going to be 4 over x minus 3. Right? 4 over x minus 3 plus 3. So it turns out the negative 3 plus 3 actually automatically cancels out. So that end up with 4 divided by 4 over x. So take my 4 divided by the 4 over x means times the reciprocal. So the 2 4 cancels out. My answer is x again. So what is going on is whenever we have f of f inverse, the composition of the two inverse function, will always equal to the same answer, which has got to be x. In that case, we show that the two function, the two function are inverse to each other. Okay, that's how I know the two functions are inverse to each other. Because if I perform a composition of the two functions, when both answers come out to be x, that means they are inverse to each other. Okay, that's what that means. All right, let's just kind of summarize everything we've done so far. Do a little bit of graphing here as well. So let's find an equation for f inverse, and we're going to start finding a couple points to help us kind of sketch our graph. So this is a very interesting problem because earlier I said parabola or quadratic function does not have an inverse function. That is true unless we put a certain restriction on the domain. If I put certain aspect on the domain, so if I'm gonna say the domain, okay, for this parabola gonna be x greater than equal to 4, that means not a restriction on domain, but set certain criteria for the domain. Then it forces me to only looking at x greater than equal to 4. Okay, this is a very weird concept. I'm not thinking about the entire graph as a whole. I'm only thinking about the domain x greater than equal to 4 of my graph. So remember, a parabola, oh, by the way, just by looking at this function, what is the vertex? Think about this. What is the vertex? X minus h plus k, right? H is 4. K is -3. So my criteria on the domain that I need to look at is x greater than or equal to 4. So that means I need to look at to the right of 4. So this entire parabola, I only need to look at x greater than or equal to 4, which is always going to be to the right of it. So that means the left side of the 4 is going to be ignored. So I'm only looking at half a parabola here. So does this half a parabola passes the horizontal line test? Yes, it does. Then I can find a formula for its inverse. Okay, so that tells me that earlier, the square root function that I demonstrated, you see, the square root function I demonstrated. Square root function, when I graphed it, was going this way, but I end up with actually a what? A parabola. Okay, so before I do this problem, I'll show you something very cool. Okay, I'm going to draw this parabola. I'm going to draw the inverse of my square root of negative x plus 3 minus 2 by not punching in another function. I'm going to draw it different way. Okay, this is what we do. All right, the word draw is right above the word program. So press second draw. All right, draw who? Go down. Draw inverse, number 8. Draw inverse of who? Inverse of y1. Remember my function was on the y1? So I think, if I remember correctly, it's on the vars. Go to the right, y vars, number 1 function. Choose number 1, y1. Draw inverse of y1 and press enter. That's the inverse. And then here is the other one. Very interesting. So the parabola I drew earlier, I actually only need half of it, not the whole thing. I actually did not need the whole thing there. So remember, I have a restriction on the domain. Negative x plus 3, okay, equal to 0. So that means x is equal to 3. So since my parabola is going to the left, that means my endpoint is going to be from left to right. My endpoint is actually at 3, 0. So when I draw my parabola, okay, see this square root right here? It was a whole entire parabola, right? But I cannot, but my invert did not show half of these. And the reason is inverse functions are interchanged between the x and y variable. So this point that you're actually looking at up here is actually 0, 3. Oh, sorry. No, I was wrong. Not 0, 3. Sorry. It's actually 3, -2. This is actually 3, -2 is my endpoint. All right, left to right ends at 3, but the y value is -2. So when I do interchange between the x and y variable, that's -2, 3. Okay, so think about this. My domain for my original function f was from -infinity to 3. When I interchange between the x and y variable or coordinates, I'm also interchange between the domain and the range. So now, if this was the domain, then the same value got to be the range of my inverse. Think about it. Down and up. It got to be from -infinity to +3 would be the range. So when I interchange between the x and y variable, okay, interchange between the x and y coordinates, I also interchange between the x and y interchange between the x and y range as the range and domain as well. Okay, so that kind of explained the reason why half of that parabola was not really there, because it doesn't quite fit into the domain and the range. Okay, now we're doing this vice versa. Start out with half a parabola, then I will actually end up with the square root function here. Guarantee it's going to happen. All right, and we'll come back and look at this. Look at this x greater than or equal to 4. So if this is a one-to-one function, then I can actually go through my 4 steps. Number 1, changing f of x to y equal. All right. Number 2, interchange between the x and y variable. All right, solve for y, move the -3 over, so that'll be x plus 3 equal to y minus 4, whole thing squared. To get y by itself, got to take a square root on both sides. Check it out. When I take a square root on both sides, square and square root cancel out, I end up with y minus 4 equal to positive and negative square root of x plus 3. All right. Let me keep going, okay? Get y by itself, move it over. So that will be y equal to 4 plus minus square root of x plus 3. Now, this is where it's interesting. Original function want me to look at x is greater than or equal to 4. So when I'm interchange between my x and y variable here, I'm also kind of interchange between this part, this variable here. It was x greater than or equal to 4. So now for my inverse function, okay, it got to be y is greater than or equal to 4. So allow me to write like this: 4 plus minus square root of x plus 3. Think about the k. Well, you know what? Rather than do that, let's do it by the graphing. If I graph 4 plus square root of x plus 3, okay, is this y greater than or equal to 4? See, starting at 4. Now, let me do the minus version of it. See, this one going downward. When we go downward, okay, see, all the y value after that point is actually not going to be what? Greater than or equal to 4. So, if I put the two pictures together, 4 plus square root of x plus 3. If I put the two pictures together, which one are we going to look at? Got to be the top one, because it was x greater than or equal to 4. Now my inverse, I have to look at y is greater than or equal to 4. So the only function that is y is greater than or equal to 4 is the plus version. So even though when I take a square root on both sides, I actually have two different functions, but only one of them, the plus one, actually give me y is greater than or equal to 4. So this is my inverse function. All right. So as far as finding 2 points, I kind of already got one, which is my vertex earlier, my starting point. So I can say 4, -3. Okay, let's just pick another number to the right of it. Let me just pick 6. How about that? 6 minus 4 is 2. 2 squared is 4. 4 minus 3 is 1. All right, so now you keep on hearing me saying interchange between the x and y coordinates and variables. So the 2 points for the inverse, I can just go ahead and interchange between the coordinates. -3, 4, and 1, 6. Voila. See right here? Let me go down. See right here? H got to be -3. K is +4. So let me do my original function as blue. My original function is blue, 4, -3. To the right, 4, down 3, 1, 2, 3, right here. 6, 1, right here. My original half a parabola, okay, goes like this. That's my f. So now my inverse, -3, 1, 2, 3, up 4, 1, 2, 3, 4, and 6, 1, 1, 6, 1 up 6. And here is my inverse. All right. So look at the blue one. Sorry, a little curve, extra curve right there. What's the domain for my original function f? Well, it got to start at, what's the x value here? 4, right? That's my starting point. It's got to be from 4, keep on going to infinity. My range, what was the y value? -3. It was down and up is from -3 all the way to infinity. Now look at this point. So for my radical function here, the starting point got to be -3, 4. So my domain got to be from -3 to infinity, just like the range. Interchange between the domain and the range. That's what this means. My range's got to be starting at 4, keep on going up. Okay, so when I interchange between the domain, interchange between the x and y variable, I'm also interchange all the domain in the range as well. Okay, all right. Hopefully this problem makes sense. Okay, drawing half a parabola, which is actually my radical functions. Okay, so this whole problem can be it's very much just like this problem that I showed you earlier. Okay, it's exactly the same thing right here. Okay, we draw it this way, but the only one to actually fit into the domain and range got to be this half a parabola that opened down rather than the whole thing. All right, that will conclude this lecture video. Thank you for watching.